Hello, my name is Stephen Roman. I'm a retired math professor. To learn more about me, if you're interested, you can visit my website at sroman.com. Today I want to talk about normal subgroups and quotient groups. It's been my experience in teaching math for almost 40 years that treatments of these subjects are not very well motivated. Usually normal subgroups are just defined. A is in a normal subgroup implies BA, B inverse is in N, and quotient groups are defined from there, and there's not much motivation. Many of my students are at first quite confused about quotient groups, so I'm going to see if I can't shed some motivational light on this subject. One of the most common themes in mathematics is making new things from old things. In group theory, for example, we have several cases of that. If G is a group, then certain subsets of G are also groups. Those are the subsets we call subgroups. And I don't need to define those for you, I'm sure you already know. If G and H are both groups, then the Cartesian product G cross H is a group under component-wise operations. And I'm sure you've seen that before. If G is a group and X is a non-empty set, then the exponential Gx, like that, this is the set of all functions from X to G. This is also a group. If you take two functions fg, their product on an element x is f of x, g of x. So as long as the range has a group structure, it doesn't matter whether the domain does or not, it's irrelevant, this will form a group. So there's three examples of producing new groups from old groups. But there's one more that is fairly straightforward. Suppose G is a group, and suppose that we partition G. So let me draw a picture. Here's G. And suppose we partition G into blocks. So we'll let P equal the set B sub I and I be a partition of G. So in this spirit that we're of making new things from old, we'll ask, is there a way to make the blocks, the set of blocks P, into a group? In other words, is there a way, can we define a block product on P. And of course we want that block product to make P into a group so that P is a group. Well, there's one, I guess, idea that should come to mind pretty quickly. If we take two blocks, say we let A and B be blocks in the partition, one way we could try to define a product would be to take an element from each block, then take their product, it's the only product we have, and find the unique block containing AB. There is a unique block because P is a partition. That's precisely why we need a partition. And let's say this block is block C. Then we define A times B to be C, the block product. Well, this is great, except there's one problem. And it might be a good idea for you to pause the video right now and see if you notice the problem as well. The problem is, what if somebody else picks different elements from the two blocks? Say alpha and A and beta and B. They'll take the product alpha beta and they'll look for the unique block that contains alpha beta, but it may be a different block than the one that contains AB. If that's the case, and it usually will be the case, then their block product will be different from our block product, and so the concept of block product will not be well defined. So block product not well defined. So the first thing we have to do is overcome this issue. Under what circumstances is the block product well defined? Or put another way, for which partitions is the block product well defined? For which partitions is the block product well defined? This is really the only problem that we have to overcome, because if we suppose for a minute the block product is well defined, then it will make P into a group. Associativity, which looks like this, follows from the associativity in G, because to take this product, we take elements from each block and we use the group product, but that's associative. And so when we reassociate this, we will get the reassociated block product. So that's associativity of block product follows almost immediately from associativity in G. Also, the block that contains the identity is the identity block. Okay. Because let's call that E. E times A is found by taking an element from each block and multiplying them together. Well, we'll just take one, the identity from E, anything from A, we'll get back that other thing, which is back in A, and so on. And inverses follow pretty easily too. If B is a block, and we'll just take an element from B, find the block that contains B inverse, let's call that C, then B times C is going to be the block containing the identity. So all we need to do is deal with the problem of the block product being well defined, and we will have found a new group from an old group. The new group, by the way, the group P, is called a quotient group. That terminology is probably not very clear right now from our discussion. It will be later, but I don't know, maybe it would have been better to call this a partition group, but it's called a quotient group. Before we continue, since we're dealing with partitions here, let me remind you wouldn't you know it, I just ran out of ink, that partitions are associated bijectively with equivalence relations. Okay. As you probably know, if you start with a partition, then the same block relation is the relation that says A is related to B if A and B are in the same block of P. That's an equivalence relation. That's easy to check. And if we start with an equivalence relation, I'm going to denote by squiggly line, then the set of equivalence classes is a partition. Remember that given an element in G, the equivalence class containing G is the set of all elements in G that are equivalent to A. There's a lot of redundancy in equivalence relations, but when we take the set of equivalence relations, that implies we're casting out duplicates, and those form a partition. And this, these two correspondences are bijective, and they're inverses of each other. So, back to this question, when is the block product of P well defined? Well, the answer is if and only if A is related to alpha, B is related to beta, implies AB is related to alpha beta. That's exactly the problem we discussed earlier. If I take A and B in two different blocks, or maybe the same block, and I take the product AB to find the product of the two blocks, and someone else takes alpha and beta, alpha from the same block as A, beta from the same block as B, and they get their product, these two, the product I got, the product they got, have to be in the same block. That will make the block product well defined. This can be expressed in words by saying that the group product preserves the equivalence relation. I'm going to just say equivalence relation instead of saying same block equivalence relation. That's always what I'm talking about, the same block equivalence relation. Okay, because these are in the same block, these are in the same block implies the products are in the same block. So this is group product preserves equivalence relation. If that happens, actually group inverses also preserves the equivalence relation. Because if A is related to alpha, then I can multiply both sides by alpha inverse using the group product preserving the equivalence relation. So I get A alpha inverse is equivalent to 1, and then I multiply again on both sides on pre-multiply by A inverse, and I'll get alpha inverse related to A inverse. So that's straightforward. Okay. So preserving the group product preserving same block equivalence relation implies the group inverse also preserves the same block equivalence relation. So in this case, if the block product is well defined, then both group operations, product and inverse, will preserve the same block equivalence relation. That's a very special situation that deserves a definition, in fact. Definition. An equivalence relation on G is called a congruence relation. That's what we're defining here. If it is preserved by the group operations. So that's product, which is a binary operation, and inverse, which is a unary operation. We don't include nullary operations. The identity is not part of this. Congruence relations are, as a general concept, we can define them for rings and modules and so on as well. As far as I know, there is no term for the partition that corresponds to a congruence relation. So I'll make one up for this talk. We'll say congruence type partition. Those are the partitions that correspond to congruence relations. That won't do any harm. I think most people would understand what that means. So where we stand now, we can have our first little theorem, which says that the following are equivalent for a partition P of G. 1, the block product is well defined, and so P is a quotient group or a partition type group. 2, the group product preserves the equivalence relation. So that means that A equivalent to B alpha rather, B equivalent to beta implies AB equivalent to alpha beta. 3, the equivalence relation is a congruence relation. Okay. Or the partition is a congruence type partition. So that's where we stand right now. But we can do better. We need to look more deeply into these conditions to try to understand what's really going on here. How else can we describe preservation under the group product, for example? This is number 2 here. Okay. Well, certainly we can see from this condition a special case. A equivalent to alpha implies we could pre-multiply both sides by a group element. We're just taking, we're taking B equal to beta, but we're applying it in pre-multiplying rather than post-multiplying. This is for all B in G. We can also post-multiply putting these together, B A C equivalent to B alpha C for all B and C in G. But if this holds, then so does its inverse, because if we start with this side, we can pre-multiply by B inverse and post-multiply by C inverse and get back here. So this is really a biconditional. This is implied by number 2 here, the group product preserving the equivalence relation. But it also implies that. So if we assume this, excuse me, we can prove number 2 here in the theorem. So let's take A related to alpha and B related to beta. And what I'm going to do, I want to produce AB in both these cases. So I post-multiply by B and pre-multiply the second one by A. Whoops, I did that wrong. Try it again. I want to pre-multiply by, I want to post-multiply this one by B, AB alpha B, and I want to produce alpha B here, so I pre-multiply by alpha. There we go. Now, these two are the same, and so by transitivity of the equivalence relation, AB is equivalent to alpha beta. Okay. And that, a preservation of the equivalence relation under the group product. Okay. So this condition here, what shall we refer to this as? Let's refer to this as the pre-post multiplication condition. It says that that pre and post multiplying preserves the equivalence relation. Okay. So that's equivalent to group product preserving equivalence relation to all 3 of the items in our theorem. So we actually have a bigger theorem here. The following are equivalent for a partition P of G. block product, well defined, and so P is a quotient group. Two, group product preserves the same block equivalence relation. 3, the equivalence relation is a congruence relation. 4, pre and post product preserves same block equivalence relation. We can do still better. Preservation under pre and post product, number 4 here, gives us the following. A equivalent to alpha implies A alpha inverse equivalent to 1. And its converse. If A alpha inverse is equivalent to 1, then A is equivalent to alpha. Okay. Also, instead of having the inverse being the second one, we can have be the first one. A inverse alpha is equivalent to 1, and this also goes both ways. So 4 gives us these two conditions, but the converse also holds. If we have 4, and A is equivalent to alpha and B is equivalent to beta, then we have A alpha inverse, let me do this, alpha inverse A equivalent to 1 and B beta inverse equivalent to 1, and so their product, alpha inverse A, B beta inverse, is equivalent to 1. I did it this way because I want A, B together. And so now I pre-multiply, or I undo this alpha inverse, move it to the other side, move the beta inverse to the other side, and I get AB equivalent to alpha beta. Okay. So these two conditions imply preservation under group product, which is number 2 of our theorem here. So these two conditions are equivalent to these 4. How should we call these? Well, if we had A equals alpha, that would certainly imply that A alpha inverse was equal to 1, and conversely, you can move elements across equal signs and turn them into their inverses, and we're doing the same thing here with the equivalence relation. So I will refer to this as elements can cross the equivalence sign, just like they can cross equal signs. Okay. So that's condition 5 here, and it's this pair of conditions here. Okay. So we now have 5 things that are all equivalent. And this is just an exercise just for its own sake. Number 5 here is quite revealing, actually. Okay. Because it says that the same block equivalence relation is completely determined, this equivalence relation is completely determined by what elements in G are equivalent to the identity of G. If we want to know whether, say, alpha and A and alpha are equivalent, we just compute A alpha inverse and check to see if it's equivalent to 1 or not. In terms of the partition, P is completely determined by the block that contains 1, which I think I'll denote by E, and I'm going to call this the special block of P. It's kind of obviously special anyway because it's if you look at the partition of a group, 1, the identity is sort of a special element, and it's in one and only one block, so that's the special block. I think that we've gotten to this point now. It seems natural to ask if the block product is well defined, so we've got all of these 5 conditions here. We know that the special block is the block containing 1. It completely determines the partition. Therefore, it determines the other blocks. What do they look like? Well, a typical block is an equivalence class containing, say, the element A. And B is in A if and only if B is equivalent to A, if and only if A inverse B is equivalent to 1, if and only if A inverse B is in the special block, if and only if B is in the set AE. AE, of course, is the set of all A little e, E in capital E, and that, as you well know, is called a coset. Okay? So, if the block product is well defined, then the partition P must be the set of cosets of the special block. We've made a huge progress here. Block product is well defined, then the partition has to be the set of cosets of the special block. So obviously the special block is special. In fact, E is a subgroup of G. It's the only block that could be a subgroup because it's the only block that contains the identity. But if A is in E and B is in E, that implies that both A is equivalent to 1 and B is equivalent to 1, and therefore AB is equivalent to 1, and therefore AB is in E. And I'll let you do the inverses yourself. E is clearly a subgroup. But it's not just any subgroup. The pre-post multiplication condition implies that if A is equivalent to 1, then BAC is equivalent to BC. And why not take C equal to B inverse? And so we get A equivalent to 1 implies BA B inverse equivalent to 1. In other words, A in E implies BA B inverse is in E. And lo and behold, we have discovered the concept of a normal subgroup. So if the block product is well defined, if we expect to have a quotient group using the blocks of the partition, then not only must all the blocks be cosets of the special block, but the special block must be a normal subgroup. Okay. So let me write that down. Block product well defined implies two things: that the special block is a normal subgroup of G, and that P is actually the set of cosets. This is well defined on P. So that's big progress. But the converse also holds. Suppose that, let me start on a new page. Well, let's work here some more. Suppose that we start with a partition and that the special block we know is a normal subgroup of G, and that the blocks of the partition are in fact cosets. Can we show that the block product is well defined? Well, if we take A equivalent to alpha, that means that A and alpha are in the same block, and we know now blocks are cosets. So A is, let's say, xh, and alpha is xk, where h and k are in the special block. And so if we take the product A alpha inverse, that's going to be xh times xk inverse, which is going to be xh k inverse x inverse. And hk inverse is in E, and E is normal, so this is going to be back in E. So in other words, A alpha inverse is equivalent to 1. So A equivalent to alpha implies A alpha inverse equivalent to 1. We can actually make this a biconditional. The block product is well defined if and only if the special block is normal and the partition is in fact the collection of all cosets. So that is the final portion of our theorem, and I'm going to write it down for you. The following are equivalent for a partition P of G. 1, the block product on P is well defined. And so makes P a quotient group. Two, the group product preserves the equivalence relation, the same block equivalence relation. So A equivalent to alpha, B equivalent to beta implies AB equivalent to alpha beta. 3, the same block equivalence relation is a congruence relation. So in other words, is preserved by product and inverses. 4, pre and post multiplication preserves the equivalence relation. 5, elements can cross the equivalence sign. So A equivalent to alpha if and only if A alpha inverse equivalent to 1, and A equivalent to alpha if and only if A inverse alpha is equivalent to 1. This one is A equivalent to alpha if and only if BAC equivalent to B alpha C. And 6, the special block is normal in G, and P is the family of cosets of the special block. When we have these conditions, then we know that our partition is the family of cosets. The block product becomes very simple. Blocks look like cosets, and to take the block product, we take an element from each coset. So why not take A and B? We form their product, and we find the coset containing that product, and we get this. So this I just simply call the coset product. Don't have to use the term block product anymore. P, as I said before, is called the quotient group. It's the quotient of G modulo E, okay, denoted this way. Or actually this way, where this is the same block equivalence relation, or same block congruence relation now. And that, by the way, the classes, the equivalence classes, are now called congruence classes. So this is mostly what we were after, but there's a little bit more to the story, because you are probably wondering, where do partitions come from? If you just take a group, G, and you just start partitioning it up in various ways, you're very unlikely to get a set of cosets, or in other words, get a well-defined group product, a block product. So where do reasonable partitions come from? The answer is they come from subgroups. If H is a subgroup of G, doesn't have to be normal, then the family of cosets is a partition of G. And I'll let you prove that yourself. Okay. So this is a natural place to get partitions, is to take a subgroup, and the identity will be in here, so H will be the special block, and then take the cosets, A1H, A2H, and so on. So we can extract from our previous theorem say the most important parts, you might say. If N is a subgroup of G, then G mod N is a partition of G. Now, in our main theorem here, not all these parts are sort of given equal weight here. The preservation of group product and the crossing of the equivalent sign and the pre and post multiplication will sort of go away. They're still important because they're all equivalent. They're equally important in that sense, but let's say they're not as common. What we're left with is the coset product. These are equivalent. The following are equivalent. The coset product is well defined. And so G mod N is a group under that product. 2, the same block relation on G mod N is a congruence relation. Three, N is normal in G. So those are equivalent. Well, finally, I think we should spend a moment looking at the broader picture. What we have shown here is that congruence relations on G define quotient groups. In fact, we write the quotient group this way. This is G mod, the equivalence class containing the identity. Okay. So there's a relationship between congruence relations on G and quotient groups. And that relationship sends an equivalent, a congruence relation to its quotient like this. And it's a bijection. It's a surjection kind of by default because we defined this quotient using a congruence relation. So this map is in this direction is surjective. But it's bijective because if we have two different congruence relations, then because the congruence relation is determined by what is congruent to the identity, two different congruence relations will have to have two different special blocks. And so when we factor out, take the quotient by that special block, like here, we're going to get two different quotient groups. So this is a bijection. Congruence relations and quotient groups. But we also have a relationship between quotient groups and normal subgroups. The quotient group is related to this is the congruence relation. It is related to the special block and vice versa, and this is a bijection. quotients come from congruence relations which have special blocks. And the congruence relations and the special blocks are in bijection because a congruence relation is determined by its special block, by what's congruent to the identity. Okay. Well, let me mark these, this one here 1 and this one here 2. The bijection 1 works for other algebraic systems. For example, for rings, we can define congruence relations on a ring as equivalence relations that are preserved by the ring operations, and we will get quotient rings. We could also do the same argument for modules, for example, or even vector spaces. Let me get some more room here. So for rings, we get quotient rings. For modules, we get quotient modules. From vector spaces, we get quotient spaces. All of these come from congruence relations on the corresponding structure. Congruence relations on rings, on modules, on vector spaces. Lattices. We get quotient lattice. You will recall that a lattice is a post set with meet and join. The meet is the greatest lower bound, the join is the least upper bound. This second correspondence, the second bijection, is in this case between quotient groups and a special type of substructure called a normal subgroup. We can do the same thing for rings. When we go through the analysis that we went through for groups, we will discover that the role of normal subgroups is played by an ideal. This is one way. When we do the same thing for modules, we will discover the special structure is not so special. It's any submodule. For vector spaces, it's any subspace. For abelian groups, it's any subgroup because they're all normal. But what happens when we come to lattices? There is no special substructure. So we do not get the same sort of correspondence for lattices that we do for groups, rings, modules, vector spaces, abelian groups. And this shows one very important thing, and that is the notion of a congruence relation is more general, in some sense more important than the notions of these special substructures like normal subgroups, ideals, and so on. It's the congruence relations that make the connection with the quotient structures. It's the congruence relations on an algebraic structure that allow us to produce another structure from the appropriate partitions. that produce another new structure from an old structure. We're lucky, in a sense, in that for groups, we don't have to talk about congruence relations. We can just talk about normal subgroups and quotients of normal subgroups. For rings, we're lucky because we have ideals that give us the quotient structures. And that's why in most undergraduate algebra classes, in my experience, congruence relations are not discussed, or at least if they are, they're discussed very lightly, because they're not needed to arrive at the concept of a quotient structure. But now you see that congruence relations really are the key to quotient structures. So I hope this lecture was interesting. I thank you for watching it, and please leave a comment. I'd like some feedback to decide whether to continue giving lectures or not. Thanks again.